Welcome to the Deep Dive, the show where we cut through the information clutter and deliver essential insights directly to you. If you're someone who loves exploring the frontiers of knowledge, maybe like we do on the Science Corner podcast, then you're definitely in the right place today. We're plunging into the, well, frankly, extraordinary life and unparalleled mind of John von Neumann. People often call him the last great polymath.
That's right. Our deep dive today focuses on John von Neumann, a polymath's legacy. And our mission really is to unpack the huge scope of his contributions. We're talking mathematics, physics, computer science, economics. We want to show you how this one individual fundamentally shaped the 20th century and, continues to influence our world right now.
Exactly. Think of this as your shortcut, sort of, to understanding the genius behind so much modern tech and modern thought. Our sources for this are pretty comprehensive. We've drawn from biographical accounts, academic works, tracing his journey from this child prodigy to a really pivotal figure in global defense. It's quite a journey. It reveals just how deep and wide a single human intellect can actually go. So let's start right at the beginning, shall we?
Yeah, to really get von Neumann, you have to go back to his early life. Born in Budapest, 1903.
Mm-hmm.
And he was just astonishingly gifted right from a very young age. I mean, by 6 years old, he could divide two 8-digit numbers in his head and converse in ancient Greek.
Wow, to stop and think about that. 6 years old. Before most kids even get basic sums, he's doing complex mental math and speaking a dead language.
It's pretty mind-boggling. It gets even more impressive. By 8, he was familiar with calculus. By 12, he'd already read really advanced texts like Borel's La Théorie des Fonctions.
That's almost unbelievable. It's a level of innate intellectual power that's just incredibly rare. What kind of education do you even give a kid like that?
Well, his education was unconventional, to say the least. His father wanted him to go into industry, practical things like chemical engineering. But von Neumann, he pursued a PhD in mathematics summa cum laude, mind you, from the University of Budapest at the same time as his engineering studies.
At the same time?
Yep. And he also studied under the great David Hilbert in Göttingen, which was like the center of the mathematical universe back then. So you see this dual track right from the start, the practical application side and the deep foundational theory.
And his memory was legendary, wasn't it? I mean, the stories, quoting entire books verbatim years later, reciting phone directories.
Absolutely. And his speed, his mathematical quickness, his peers called it awe-inspiring. There's that famous fly puzzle story.
Oh, yeah, tell us that one.
Well, someone posed this complex problem. Looked like it needed summing an infinite series, tricky stuff. And von Neumann just instantly gave the answer. He saw a simple shortcut nobody else did.
It just highlights the sheer speed and, I guess, efficiency of his thinking.
It really does. It speaks to a unique kind of cognitive processing. And his work habits were interesting, too. Apparently, he did some of his best work in noisy, chaotic places.
Really? Not needing quiet?
Seemingly not. Impervious to distraction. And there are stories he'd go to sleep thinking about a problem and just wake up with the solution fully formed, like his brain was working nonstop, even subconsciously. Host, speaker,
Okay.
seeker.
Okay, so with this incredible mind, how did he start applying it? Let's get into his impact on mathematics itself. It sounds like he was building the very foundations. Indeed, he started young. At just 19, he published significant papers, including a new definition of ordinal numbers. That's pretty advanced stuff. Then, in his 1925 doctoral thesis, he tackled Cantor's set theory. He essentially provided an axiomatization, a rigorous rulebook.
What did that achieve, practically speaking? Well, it was huge. He created a more robust, paradox-free framework for set theory. He introduced the axiom of foundation, the notion of class. These implicitly got rid of contradictions like Russell's paradox, which were really shaking the foundations of math at the time.
Okay, so he's making math more solid, more consistent. But then what happened when that consistency itself was challenged? I know Kurt Gödel came along with his incompleteness theorems.
Right, and this is fascinating. Von Neumann was initially involved in proof theory, trying to establish that consistency. But when Gödel published his first incompleteness theorem, von Neumann grasped its implications almost immediately.
Which were?
That any sufficiently powerful axiomatic system can't actually prove its own consistency. It was profound.
Yeah.
And for von Neumann, this was a major turning point. It seems it convinced him that chasing absolute certainty in pure foundational math might be, well, a bit futile.
So he shifted his focus.
Drastically. He turned much more towards applied problems, where mathematics could be a tool to solve real-world challenges.
But he still left a massive mark on pure math even after that shift, right? I read about his work in ergodic theory.
Oh, absolutely.
Yeah.
His 1932 papers laid fundamental contributions there. Ergodic theory is basically about how systems behave over long time scales. Think gas dynamics, chaos theory. One expert even said that work alone was enough for mathematical immortality.
Wow.
And then there's functional analysis and operator algebras. He defined abstract Hilbert spaces axiomatically, developed the spectral theory of operators. He became the undisputed master of that field for like 2 decades.
Hilbert spaces, that connects to quantum mechanics later, doesn't it?
Exactly. His work there led to what some call his most profound invention in pure mathematics, von Neumann algebras. These are complex abstract structures, but they turned out to be essential for understanding quantum systems. They're still fundamental in modern analysis. He wasn't just solving problems, he was creating whole new mathematical worlds.
He even founded something called continuous geometry, where dimensions aren't just whole numbers.
That's right, where the dimension of a subspace could be any value between 0 and 1. A pretty wild idea. And it required inventing new concepts to even describe it, like von Neumann regular rings. The depth and breadth is just staggering.
Okay, so having built these incredible mathematical tools, it seems almost inevitable he'd turn to physics, especially that weird new field, quantum mechanics.
It was a natural fit. His 1932 book, Mathematical Foundations of Quantum Mechanics, was revolutionary. He established the rigorous mathematical framework, what we now call the Dirac-von Neumann axioms. He essentially translated the physics into the language of Hilbert spaces and linear operators.
Making it more consistent, more mathematically sound.
Precisely. It provided a unified language, made the theory much more rigorous and, in a way, accessible to mathematicians.
But then he waded into the really deep philosophical waters, right? The measurement problem.
He did. He famously analyzed the measurement problem, what happens when we measure a quantum system. And he reached a controversial conclusion that maybe the collapse of the wave function is caused by the consciousness of the observer.
Whoa. That's pretty out there for a hard-nosed mathematician.
It was, and still is. People like Eugene Wigner agreed with him, but it never became the mainstream view among physicists. But it shows his willingness to tackle the absolute deepest conceptual challenges, even bordering on philosophy.
And his other quantum work, it's still relevant today.
Absolutely fundamental. Concepts like von Neumann entropy, the density matrix formalism. These are cornerstones of modern quantum information theory. Crucial for understanding information in quantum systems, quantum computing, all of that.
Okay, but his physics wasn't all abstract theory. You mentioned World War II.
Right. During the war, he made really significant contributions to fluid dynamics, vital for understanding explosions and ballistics. He worked on the Taylor von Neumann-Sedov blast wave solution, the ZND detonation model for explosives, and he developed something called the artificial viscosity algorithm. This was key for early computer modeling of shock waves, practical, applied physics.
It's just amazing how his abstract math always found these concrete applications. And maybe nowhere clearer than in economics. He practically invented game theory as a mathematical field.
He really did. He proved his minimax theorem back in 1928, laying the groundwork. But the big splash was the book he co-authored with Oscar Morgenstern in 1944, Theory of Games and Economic Behavior.
What was so special about that book?
It extended game theory to situations with imperfect information, multiple players, much more like the real world. And, crucially, it declared that economics needed different mathematical tools, not just calculus, but functional analysis, things like convex sets, fixed-point theorems. It fundamentally changed how economists thought about strategy and competition.
And the impact was huge, right? Influencing Nobel laureates.
Absolutely. His model of an expanding economy, using his own generalization of the Brouwer fixed-point theorem. Some call it the greatest paper in mathematical economics. It directly influenced giants like Kenneth Arrow, Gerard de Broglie, John Nash. They used von Neumann's mathematical toolkit in their own Nobel-winning work on economic equilibrium. He literally built the mathematical language for a lot of modern economics. And he wasn't just theorizing about economics, was he? Linear programming.
Right. He invented the theory of duality in linear programming, super important for optimization, like allocating resources efficiently. There's a great story about George Dantzig, who developed the main algorithm for linear programming, the simplex method. Dantzig presented his work to von Neumann. After just a few minutes, von Neumann apparently launched into this hour-long, completely off-the-cuff lecture on the underlying theory of duality, which Dantzig hadn't fully grasped. He even suggested an early version of a different method, the interior point method, decades before it was properly developed. That just shows his incredible ability to grasp the essence of a complex system almost instantly. Okay, let's shift gears to computer science. This is where his name is probably most famous, the von Neumann architecture.
Absolutely. That 1945 paper, the first draft of a report on the EDVSC, was seminal. It described a computer architecture where both the instructions, the program, and the data are stored in the same memory space.
Which is how basically all computers work today, right?
Pretty much.
Yeah.
Now, the core concept might have originated with Eckert and Mauchly, who were building the E9IC and EVAIC. There's some debate there. But von Neumann's report codified it, explained it clearly, and it became the blueprint. He then designed the IAS machine at Princeton, which heavily influenced early commercial computers like the IBM 701. He truly shaped the digital age's foundation.
And he wasn't just about the hardware architecture, algorithms too.
Oh, yes. He invented the merge-sort algorithm in 1945, still a very efficient way to sort data. He made key contributions to the Monte Carlo method, using randomness to solve complex problems. He even worked on generating pseudorandom numbers. He came up with the middle square method, though he famously quipped that anyone trying to generate random numbers arithmetically was in a state of sin.
Huh. Because true randomness is hard to achieve algorithmically.
Exactly. And he was one of the very first people to seriously discuss time complexity, basically. How long algorithms take to run as the input size grows. That's fundamental to computer science theory today.
His foresight seems almost unreal. I read his work on self-replication predated Watson and Crick discovering DNA.
It did. His mathematical analysis of self-replicating machines was purely theoretical, of course, but conceptually groundbreaking. He and Stanislaw Ulam essentially created the field of cellular automata simple rules, creating complex patterns, like Conway's Game of Life later. They designed a theoretical 2D automaton that could reproduce itself.
Wow. Laying groundwork for artificial life and complex systems research decades early.
Precisely. And his influence was huge in scientific computing. He developed von Neumann's stability analysis, crucial for making sure computer simulations don't blow up with errors. Contributed to backward error analysis, too. Under his guidance, Los Alamos became a real powerhouse in computational science.
But then he applied this computational power to something massive, global weather systems.
Yes, he got very interested in weather prediction. Saw parallels with the complex physics calculations from the Manhattan Project. In 1946, he started the Meteorological Project at the Institute for Advanced Study. By 1950, he and Jule Charney had written the world's first climate modeling software and ran the first numerical weather forecasts on the ENIAC computer.
The first computer weather forecast.
The very first. It was pioneering stuff, laying the foundation for all the climate models we rely on today.
And this led him to think about climate change itself.
Incredibly presciently, yes. In 1955, he observed that human activity, specifically burning fossil fuels and releasing carbon dioxide, might already be causing global warming.
In 1955.
1955. He even speculated about geoengineering, like spreading dark material on ice caps to melt them, but also warned very clearly about the potential military uses of weather control. He saw both the power and the danger.
That foresight is just stunning. And it connects to another concept he's credited with, right? The singularity.
Yes, Stanislaw Ulam recalled von Neumann talking about the ever-accelerating progress of technology.
Yeah.
He apparently discussed a point in the future, beyond which human affairs, as we know them, could not continue. That's the core idea of the technological singularity, decades before it became a popular concept.
Mind-blowing. Okay, finally we have to touch on his defense work. It was significant, especially during the Cold War. It started with the Manhattan Project.
It did. He became an expert in the physics of explosions, which made him invaluable. He made absolutely critical contributions to designing the complex explosive lenses needed for the implosion-type plutonium bomb, the Fat Man bomb used on Nagasaki.
Calculating that it would actually work?
Exactly. He calculated it would work if the implosion shockwave was symmetrical to within about 5%. Hugely complex calculation back then. He was also on the committee that selected Hiroshima and Nagasaki as targets. His first choice apparently was Kyoto because of its industrial and cultural significance, but it was spared.
And he witnessed the Trinity test.
He did. Famously estimated the bomb's yield just by watching the blast wave and dropping pieces of paper. Kick, back of the envelope physics. He later received awards for his wartime service.
After the war, his influence in defense circles just grew, didn't it? He became a major figure.
A superstar defense scientist, as some called him. He consulted for the CIA, the Atomic Energy Commission. He held the highest official government position for a scientist.
How did he manage that transition from pure science to high-level policy?
His sheer intellectual power, his ability to synthesize complex information and explain it clearly, made him indispensable. He played a really crucial role in pushing for and designing the U.S.'s first intercontinental ballistic missile programs, the ICBMs.
Convincing Eisenhower.
Yes, he argued forcefully that developing compact hydrogen bombs deliverable by long-range missiles was absolutely vital for national security in the Cold War era, and he convinced President Eisenhower. The Atlas and Titan rockets, which his committees recommended, became mainstays of the U.S. nuclear deterrent. His scientific advice directly shaped Cold War strategy. He genuinely believed these developments were essential.
It's just an incredible span. John von Neumann's legacy is truly immense. It stretches from the most abstract math to the most concrete, world-changing technologies.
He was an intellectual force of nature, wasn't he? Always synthesizing, connecting different fields, looking for the underlying logic and the potential applications.
And the person behind the intellect sounds fascinating, too. The quick wit, that incredible memory, but also hints of self-doubt.
Yeah, it's striking. You have people like Hans Bethe, a Nobel laureate himself, wondering if von Neumann was a superior species. Claude Shannon, the father of information theory, called him the smartest person I have ever met. Yet, apparently, von Neumann himself once mused that maybe he'd be forgotten, while Gödel, with his one earth-shattering theorem, would be remembered forever.
It adds a human layer to the legend, so reflecting on it all. Von Neumann didn't just build the tools of the future, he saw their implications coming. Climate change, the singularity, weaponized weather.
He really did. His warnings were remarkably prescient.
Which leaves us with a pretty profound thought, doesn't it? Given those warnings and the accelerating pace of technology he predicted, what responsibilities do we have today? How do we make sure that all this incredible power serves humanity rather than, overwhelming us? That's definitely something to think about long after this deep dive is over.